Can you hear me? Yes? Okay, so hello, everybody. Guys, I'm Carles Cantero. I'm a postdoc researcher in the University of Geneva and the Observatoire of Geneva. And I'm going to talk about a novel project, a very recent project that is called SpeckleNet, a deep learning framework for speckle modeling. So first of all, I would like to highlight that this year, we celebrate 20 years of ADI processing, post-processing, basically by classic ADI by Marat. So let me just summarize how it works. So when we have an ADI cube with our speckle noise, normally we take the median of this cube to just do the PCF subtraction, and then we just derotate with the parallactic angles, to collapse and have our detection map. This is normally how it works. So in this full process, we can identify two main actors that are super important for our performances. First of all is the detector. We need a detector, and then the noiser. In this point, I would like to highlight also that we have a new poster, the number 14, in which we find candidates, 13 unreported candidates with a new detector that we found. But SpeckleNet is not about a detector. It's about how we denoise the image, how we really take the distribution of a speckle noise to the noise. So in these 20 years, we have made a lot of progress, of course. We have all these huge of algorithms, ADI post-processing algorithms, but there is a pattern here, an interesting pattern, which is most of them are low rank or PCA related somehow. This means that PCA was super nice all these years, and it's still the standard algorithm for high contrast imaging surveys. So if we come back to our detector and the noiser, how it changes. So now what it changed is basically the noiser, how we model the speckle noise. There you have seen the PCA, right? So let's put it inside there and how it works. So basically, we take the median image. Again, here, we subtract the median image. And then this cube of residuals, we construct these huge matrices of pixels, which is basically the input of the single variable decomposition. What we want to do with this is just decompose this huge matrix in principal components that take or have captured orthogonal or independent information by variance of our data set, of our data. Then you can use these principal components to do a projection and reconstruction of our images. But the point here is not that. My point here is this little black space, what we call this latent space. This projected space that is orthogonal and linear. This is so important. PCA is linear. It's ordered by the amount of variance, and it only captures the dominant speckle variability. That is what we want, right? But it also is capturing the planet signal, the planet subtraction. And this is something that is very important in this work. There is another pattern here in these 20 years. Deep learning has emerged as a very important actor here in the last years. Trying to improve this planet subtraction, trying to improve the detector also, different works. But here is where SpeckleNet comes out. The idea of SpeckleNet is to use a standard state-of-the-art generative models trying to use all these things. So we have there is a convergence, we can call it convergence, to three pillars that SpeckleNet uses. The first pillar is that we have knowledge, 20 years of knowledge about how this speckle noise is distributed, spatial correlation, temporal correlations, atmospheric variability, and how this change. And this is something important. The second, and maybe the most important pillar of SpeckleNet is that now we have the technology. Maybe 20 years ago, no, or 15 years ago, no. But now we have the technology to really go to nonlinear latent spaces and to capture the real manifold of the speckle data. And with that, we can use real technology, tested technology that we are not using here in high contrast imaging. And the third pillar is that we're starting to have big data, archival data, high contrast imaging service that we can use for this technology. So here is where it is SpeckleNet, and I would like to explain you how this, what we have right now, okay? So we are using sphere shine data. We are using autoencoders and something of diffusion models I will explain you later. And we are also using a spatial correlation of speckle noise. But the idea is to move forward in the future with all this panorama you can see here. SpeckleNet is based on a proof of concept, very nice proof of concept that is called Construct. It was published 2 years ago. And I will explain you now how Construct is based and how we improve Construct in this sense of SpeckleNet to have big data. Basically, the principle of Construct is trying to replace PCA by a nonlinear reduction model, which is an autoencoder, to do the PSF model. So here you can see a comparison. So you have the PCA, you have your image, okay, that you want to model. Then you pass it through the singular value decomposition with your principal components, and you reconstruct the image, okay? This is linear space again, and you are modeling the planet too, okay? In Construct is another idea. Instead of having the full image, you work by patches, small patches, and the projection and reconstruction part is not done by PCA, it's done by neural networks, okay? That's why we have non-linear space, because neural networks can capture these non-linear spaces. But there is another thing. Instead of reconstructing the patch itself, Construct is using what we call in deep learning image in painting. Image in painting is basically a technique that you mask some part of your image, and you teach the neural network to reconstruct this part based on the knowledge you have in the image, just the speckle pattern. So now imagine that you have an exoplanet there. If you mask the exoplanet, there is no exoplanet signal while training the neural network, okay? So that's a little bit the idea of Construct. It's a self-supervised learning, of course, and Construct is using an EC2 data, about 30,000 patches as a training set, okay? And it's using an architecture, an autoencoder that is called convolutional unit. I don't want to enter into details here, how the unit is working and why we have these skip connections, but if you have questions, we can talk about that. So when the autoencoder is trained, how we do this denoising thing? How do we do the inference part? So again, here we have our denoiser, the cube, and we select patches. We mask the patches in all the temporal cube. These are the patches that are in the input of the autoencoder, and the autoencoder basically is just filling the patches about what he has learned about the speckle noise. Then we have PSF subtraction, in that case it's patch subtraction, and there is a temporal regression that they are doing about to take into account biases in the autoencoder, and we have our speckle model based on only in autoencoders, not in principal component analysis. So what we have with that in SpeckleNet? The idea is that we strongly think that the Construct idea is a very nice proof of concept that already surpasses PCA, but we think that we can really, really improve it. Now we are working, as I told you, with sphere data. We constructed a toy data set about 15 million patches of the same kind of data. You can see it here. But also we have atmospheric conditions like the seeing, their mass, the stellar radio, of course the separation of the patch to the star, these kind of features that we can use to teach farther away the neural network to really understand this manifold we want to understand, okay? We are not using the same unit as Construct. We are improving the unit as one thing that is unit plus plus. Again, we can talk about unit plus plus, but now it's not the point. And then we are using the unit plus plus and adding this conditional learning. We are conditioning the learning about the atmospheric features and the separation. So you will see now really preliminary results of a SpeckleNet about real systems in a sphere. So this, for example, this is one example. So each row is a different epoch of a sphere for this system HR 8799. You can see, I don't know if you can see it, I guess so, the name of the algorithm, construct, SpeckleNet unit, and also I am adding the Loki PCA with 10 principal components and PCA with 20 principal components, okay? So these are signal-to-noise ratio maps after all the ADI processing. And you can see, well, the signal-to-noise, how is the recovery? So I put the green stick where the recovery is better, the two first better, and the red stick, the red cross, let's say, when it's worst, okay? So you can see that the SpeckleNet is, for example, in the first row is better, but there is PCA is better. So for this system, we have these results. For beta peak, we have these other results. There is something important here to highlight maybe, that for the beta peak, you can see that the SpeckleNet is not modeling properly as PCA the disk. No, there is no disk there. And this is something that we expected because in our data, we are not we are not proposing data from disk. So this is something that we have to improve. Okay? This is another result for this system. And this, we took, just to see the preliminary contrast curve, we took 20 cubes that were not used for the training from the sphere shine data, and we were computing the mean contrast curve of these 20. So as you can see here, the SpeckleNet unit ++ with conditional learning is a little bit better, and the blue one also. But this is something that we expected a little bit more, better gain of contrast in that sense. Of course, we want to compare with another algorithms. We want to add here annular PCA. We would like to add here, for example, the amazing force of Marcus, and try to understand, no? But we are in this point right now. This is a particular IDI case that I want to highlight. So there you have the contrast curve again, the throughput calculated, and this is the standard deviation of the residual flux and the mean of the residual flux. So what you see here, for example, in the contrast curve, you see that PCA is reaching a little bit better contrast, right? But if you see the throughput at small angular separations, the neural network-based models are having a very nice throughput. But at the same time, the reconstruction of the speckle noise is not that well at this angular separation for neural networks. So parallel developments, we are trying now to add the temporal dimension to these kind of models to see how it works. And this is important, and with this I stop. So this kind of models allows us to have flexibility with data. So what we want to do is to try to say if we can adapt these models directly to Saxo Plus. So we are simulating Saxo Plus high contrast imaging with normal Saxo high contrast imaging. So this is something that is in parallel working with this kind of models because they are so flexible. So thank you so much, and with this I conclude.
Questions? Yeah.
Hi, Aniket, here in the back on the left. Okay. I was curious, how close are you to the photon noise limit for the reductions that you've already done for HR 8799?
We didn't calculate this yet, so, okay. But we have to do it actually. Yeah.
I have a question for this creation of the patches. So you say that you train the network by adding observing conditions and these kind of things. If you split up the data in patches, you lose the locality information. So the network doesn't really know if it's close to the star or if it's far away. Do you add this as an additional information like the seeing conditions?
You mean the separation? To the
separation, or even even the precise position on the detector, because in principle, the speckles are different depending on where you are.
Yeah, we are actually, I don't know if yeah. Here. So here we have the separation. We have to add, for example, the angle of the patch. But yeah, we have all these features, and we can add more features. We can do a hyperparameter tuning or feature tuning to try to do this. But at this time, we are trying to do this. Also, we have to do like feature importance, because of course, I guess the temperature, the humidity, the current time maybe is not so much relevant with compared with what you said, the separation and these things that are super relevant, super correlated. But yeah, we have to do it.
Okay, thank you again.
Thank you.